On the morning of July 27, 1866, a small fishing harbor in Newfoundland waited beneath a pale Atlantic sky. Wooden houses followed the curve of the shore. Boats rested close to the water. The community was called Heart's Content, and until that summer its daily life had been shaped by the ordinary distances of a North Atlantic settlement. Then, an enormous steamship appeared in the bay. The Great Eastern was unlike anything normally seen from the harbor. 4 funnels rose above its long iron hull, 6 masts broke the skyline, and deep inside the ship lay thousands of kilometers of telegraph cable. The vessel had crossed from Ireland, carrying the final working link in an idea that engineers, investors, sailors, and electricians had pursued for years. A wire beneath the Atlantic Ocean. Heart's Content is now part of Newfoundland and Labrador, Canada. In 1866, however, Newfoundland was a separate British colony. It would not join Canada until 1949. The cable story belongs first to that older Newfoundland world, even though the place later became part of Canada. Before the cable, the Atlantic imposed a simple delay. A letter, newspaper report, business order, or government dispatch had to travel aboard a ship. Weather, distance, and sailing schedules controlled the pace. Steamships had made the crossing more dependable, but information still moved with a physical vessel. On land, telegraph wires had already changed that rhythm. A message could be turned into electrical signals, sent along a wire, received elsewhere, and written down again. In Newfoundland, telegraph lines had begun to spread during the 1850s, linking coastal points and helping move news toward mainland North America. One of the attractions of Newfoundland was simply its position. It reached far into the North Atlantic, closer to Europe than the major cities farther west. If news could arrive there first, telegraph wires could carry it onward faster than the ship that had brought it. Before a permanent ocean cable existed, this geography already created a race between steam and electricity. News vessels could meet incoming ships, collect reports, and transfer them to telegraph stations on land. From there, the information could move ahead through wires, while the original steamer continued toward port. The system saved time, but it still depended on a vessel for the Atlantic crossing. The ocean remained the great interruption. The first attempt to remove that interruption had briefly succeeded in 1858. A cable was laid across the Atlantic and messages passed through it. The achievement was real, and for a short time it was celebrated as though the problem had been solved. The line soon weakened and failed. Electrical stresses, manufacturing defects, handling, and the limits of contemporary knowledge all became part of the investigation that followed. The brief life of the 1858 cable mattered because it separated 2 questions that had once seemed inseparable. It showed that a signal really could cross the Atlantic through a submerged conductor. The remaining problem was how to build, lay, test, and operate a cable reliably enough for that connection to last. Years passed before another serious attempt was ready. Better cable construction, improved electrical understanding, stronger testing procedures, and a remarkable ship all became part of the solution. The Great Eastern had originally been designed as a giant passenger vessel. Its commercial career disappointed its owners, but its enormous size made it unusually useful for cable work because it could carry an entire Atlantic cable in one ship. The conversion changed its silhouette as well. One of the original 5 funnels was removed to make room for cable equipment, leaving 4 during the Atlantic cable expeditions. In 1865, the Great Eastern began laying a new cable from Ireland toward Newfoundland. The cable paid out behind the ship for more than 1,000 miles before it broke and disappeared into deep water. Repeated efforts to recover the lost end failed, and the ship returned without completing the connection. The setback did not end the project. Another cable was prepared for 1866, while the lost 1865 line remained somewhere on the ocean floor. The cable itself looked simple from a distance, but every layer had a purpose. Copper wires formed the conducting core. Insulating material kept the electrical signal separated from seawater. Preserved fiber coverings and iron wire armor helped the cable survive manufacture, coiling, handling, and the long descent from the ship into the Atlantic. Near shore, where anchors and fishing activity created additional risks, the cable could be made heavier and more strongly protected. Inside the Great Eastern, the cable rested in enormous circular tanks. Crew members could walk around the great coils while the ship moved, watching for a turn that might catch or rise incorrectly. The cable had to leave the tanks smoothly. A kink, sudden strain, or fault could waste days of work and send kilometers of expensive cable toward the seabed. On deck, paying-up machinery controlled the line as the ship moved west. The cable passed through guides and brakes before slipping over the stern. Too much restraint could break it. Too little could waste cable or allow it to fall badly. The ship's speed, the depth of the water, the amount of cable already hanging behind the stern, and the tension measured on deck all mattered at the same time. Electricians tested the cable continuously so that a hidden failure would not travel unnoticed behind the ship. The mechanical work and electrical work were therefore inseparable. The cable had to survive the ocean physically while remaining alive as a conductor from one end to the other. The electrical problem was as important as the mechanical one. A signal that had traveled across such a long submarine cable arrived extremely weak. Ordinary telegraph instruments were not always sensitive enough. William Thomson developed a mirror galvanometer that could detect tiny currents. A small mirror moved with the electrical signal, and a reflected spot of light shifted across a scale. Minute electrical changes became visible movement. The instrument demanded patience. A weak current reached the receiver, and the reflected light moved. An operator interpreted the deflection while another operator could write the signal down. The motion might be small, but the meaning behind it could be enormous. A price, a shipping instruction, a newspaper report, a family message, or a government dispatch. The cable did not make communication automatic. Every message still passed through human hands. Words were encoded. Speed came from joining many careful tasks together. The process could be slow by later standards, but compared with a ship crossing the Atlantic, it changed the meaning of distance. During the 1866 voyage, the cable was tested while it was being laid. Messages could pass through the line back toward Ireland, confirming that the connection behind the ship remained alive. Day after day, more cable slipped over the stern and disappeared into water that deepened beneath the hull. Thousands of people gathered around the harbor to watch. The final section of cable was brought toward shore and connected to a temporary station adapted inside a rented local wooden dwelling. For the community, the scene joined familiar objects with extraordinary machinery. Fishing boats and wooden buildings stood beside coils of cable, work crews, and telegraph instruments, while the largest steamship in the world waited in the bay. On the landing day, Heart's Content did not yet have a purpose-built cable office. The company had adapted a rented wooden dwelling near the shore as a temporary station. Another rented house was used when the second cable came ashore in September. A purpose-built wooden cable office followed in November 1866. The large red brick station that survives as a historic site belongs to a later phase and dates from the 1870s. In July 1866, the importance of the place came not from grand architecture, but from the line entering it from beneath the sea. A transatlantic message now moved through several connected systems. A message originating in Europe could travel by land telegraph toward the Irish cable terminal. There it was converted into signals sent through the submarine cable. At Heart's Content, operators received those faint electrical changes, translated them back into written language, and passed the information onward through other telegraph connections. The ocean leg no longer depended on a steamship carrying a sheet of paper. News that had once taken more than a week to cross the Atlantic could begin arriving through the cable in minutes. The wider network still required relays, operators, local lines, and careful transcription, but the largest physical gap had changed from a voyage into an electrical connection. The work inside the temporary station was repetitive rather than spectacular. Instruments had to remain adjusted. Signals had to be watched closely. Messages had to be copied accurately. A weak or uncertain deflection could not simply be guessed. The value of the system depended on attention to small movements and small marks. The temporary cable station, therefore, developed its own quiet rhythm. One operator watched an instrument while another wrote. Messages were checked and handed onward. A desk could hold paper, ink, instruments, and the ordinary evidence of a long shift. Outside, the harbor continued with boats, weather, and fishing work. Inside, information from another continent arrived as tiny movements of light and current. There was also a practical difference between receiving information and understanding its importance. The electrical signal did not announce whether the words concerned a market price, a ship, a newspaper, or a government office. To the cable, each message was another sequence to be transmitted faithfully. The drama belonged elsewhere. At the station, reliability depended on routine. The success of July 1866 was not the end of the summer's cable work. The Great Eastern later returned to sea to search for the cable lost in 1865. After repeated grappling attempts, the older line was recovered from deep water, completed, and brought into Heart's Content in September. The station then had 2 working Atlantic cables instead of 1. That second connection mattered because a single cable could fail. Submarine lines were difficult to inspect and repair, and every fault could interrupt communication. Multiple cables gave the system greater resilience. Over the following decades, additional Atlantic cables came ashore at Heart's Content. Between 1866 and 1894, 6 different cables connected the Newfoundland terminal with the Irish side of the system. The town changed around the work. Cable employees arrived from abroad and from Newfoundland. Company buildings and housing appeared. A permanent station was constructed in the 1870s, and later staff houses reflected the growing importance of the operation. Heart's Content remained a fishing community, but it was also becoming an international communications center. The contrast was unusual. A place with a small harbor and a modest population became part of a network linking financial markets, newspapers, governments, shipping interests, families, and businesses on opposite sides of the Atlantic. Messages that concerned large cities could pass through a quiet Newfoundland settlement on their way from one continent to another. The later cable station looked more substantial than the first wooden office. Brick walls, workrooms, instruments, cable entries, desks, and staff routines gave physical shape to a system that was otherwise mostly invisible. The Atlantic cable itself disappeared beneath the water almost as soon as it left shore. Most people never saw the thousands of kilometers lying on the seabed. They saw the station, the operators, and the messages that arrived. By the late 19th century, the cable network had become less astonishing and more ordinary. That was a sign of success. What had once attracted crowds to the shoreline became infrastructure. Operators reported for work, equipment was maintained, and messages arrived and left according to established routines. New cables increased capacity and reliability. The extraordinary achievement settled into ordinary work. As those lines multiplied, the character of the system changed. The first successful cable had been a fragile bridge, whose loss could silence the connection. A network of cables offered more paths and greater capacity. The ocean was still difficult terrain for engineering, but the idea of an Atlantic telegraph had moved from experiment toward permanent service. The station continued operating for almost a century. Technologies changed, competing cables multiplied, and radio later offered another way to cross the Atlantic without a physical wire. Heart's Content remained part of the cable world until the facility finally closed in 1965. The surviving station preserves that later history, but the central moment remains the summer of 1866. A ship entered the harbor, a cable came ashore, and a rented wooden dwelling adapted for telegraph work became one end of an electrical bridge beneath the ocean. Late in the day, the harbor would have returned to quieter sounds. Inside the temporary station, an operator could watch the receiving instrument and wait for another faint movement. The signal itself had crossed darkness that no operator could see. It had traveled through copper sealed inside protective layers, down the continental slope, across the deep Atlantic floor, and back toward land. There was no light beneath the water and no visible path on the surface. The connection existed as a cable hidden under kilometers of ocean. A spot of reflected light moved across the receiver. A mark was written down, and another signal followed. For centuries, the Atlantic had measured communication and voyages. In Heart's Content, during the summer of 1866, that measure changed. The ocean remained just as wide, but information no longer had to cross it at the speed of a ship. The Atlantic did not become smaller, only the time between its shores had changed.